Hey folks, I'm just going to write up the solutions for these 3 review thinking questions that you were working on this afternoon. Make a little video. Now, a lot of people approach this one in kind of a much more complex way, I think, than what you need. And we know that if they intersect in a single point, a number of people kind of said, oh, okay, well, I'm going to need to figure out some way of making this identity matrix with this goal. And that actually will work, that if you sort of did any kinds of operations, like matrix operations here, and you could do kind of any crazy nonsense and get back to different equations for these other two. Like these are kind of trivial planes, saying like this would be y equals 4 and this would be z equals 14, just like the flat plane that's parallel to the xy or xz axes. But we could kind of rewrite these, so you could do that, and some people were making good progress with sort of going backwards. And you might say, like, I'm going to do row 3 times 4 and row 2 plus row 3, and just kind of like add things in and like mess it back up to try to get back to having like this row at the start. So that is for sure an option, to try and kind of get like this at the top row and then 2 other rows here. Like do any kind of nonsense that you want to work backwards to that. You for sure you can. I think it's personally a lot easier to kind of plan that what would I know if I had those, if I had 3 planes that intersect in a single point. So here, if they intersect in a single point, I know that that means, that's a weird arrow, that that's case number 8, and I would know that n1 dot n2 cross n3 would not equal 0. I could do that test, and if they intersect at this point is on plane 2 and plane 3. So I need 2 other planes that have that point on them, and also that would have this property that if I did that coplanar check with the normals, that would not equal 0. It could be anything else other than 0. So I'm just going to make up some planes. I'm going to make up some planes. Plane 2. I'm going to say that this plane is AX plus BY plus CZ plus D equals 0. My only restriction on A, B, and C is that they can't be scalar multiples here. These planes can't be parallel to the plane I'm already given. So, okay, I can pick anything other than a scalar multiple of 1, 1, negative 1. Anything else. So I'm going to pick 2x minus 3y plus 4z plus d equals 0. I also know that this point, 7, 4, 14, is on my plane. So if I sub in that point, I can solve for d. So 2 times 7 minus 3 times 4 plus 4 times 14 plus d equals 0. So I'm going to get d equals 14 minus 12 plus 4 times 14. D is negative 58. So plane 2 is going to be 2x minus 3y plus 4z minus 58 equals 0. So remember, there's an infinite number of planes that pass through here. If you have an infinite number of anything, you don't have to be super picky about which one you're getting. And similarly, I'm going to find for plane 2, or plane 3, pardon me. Kind of similar plan. I know that ax plus by plus cz plus d equals 0. And now my restriction on the normal ABC is just that it can't be a scalar multiple of the normal from plane 1 or the normal from plane 2. So that's okay. I might say that this is x minus 2y plus z plus d equals 0. So the normal here is 1, negative 2, just going to make that look more like a 2 and less like a z, and 1. Now I'm going to sub in the point just like I did before. 1 times 7 minus 2 times 4 plus 14 plus d equals 0. And 7 minus 8 plus 14, and then bring it over to the other side. D is negative 13. So this equation is x minus 2y plus z minus 13 equals 0. So here we go. Now the problem is these planes, for sure, they all intersect at this point. They all pass through that given point, 7, 4, 14. I don't know, however, if those planes are going to be case 8, where they all intersect in a point, or the other case where they intersect along a line, and all of the planes would go through that line, and that line would just happen to have the point 7, 4, 14 on the line of intersection. And the way I'm going to check which of those cases it is, I'm just going to do this, coplanar check. So I know that N1 is 1, 1, negative 1, N2 is 2, negative 3, 4, and N3 is 1, negative 2, 1. So I'm going to check N1 dot N2 cross N3 and see what that gives me. So here I have just done, because I'm really out of space, I did N2 cross N3 just on some scrap paper, and I got that my cross product here was 5 to negative 1. You will get a different thing because you will have come up with different equations. So here, 1, 1, negative 1 dot 5 to negative 1. So here I have 1 times 5 plus 1 times 2 plus negative 1 times negative 1. So that is equal to 8, which is not 0. So if it's not 0, that's case number 8. If I had gotten a 0 here, just kind of by like terrible bad luck, I just would have gone back and gotten rid of one of these planes that I had found and just found a different plane. Find a different equation of a different plane and double check that again. There's, and like I said, an infinite number of different planes that you could pick. The odds of you getting 0 are pretty slim. You do need to check it. If you got a 0, you could just like adjust one of the coefficients. That'll change your D value, kind of play around with it a little bit just to get a slightly different number when you do that check. The next one, rectangular box has these sides, length 1, 2, and 3. This is kind of similar to the one that we did in class today. So I'm going to say that H is going to be 0, 0, 0. So we're gonna look at this as like the X and the Y and the Z axis there. So I don't know which of these I really need, probably not all of them, but this will be 2, 0, 0, F will be 2, 3, 0, G will be 0, 2, 0, A is 2, 0, 1, B is going to be 2, 3, 1. Oops, and this is a 3 in G. I made a mistake there. And C is going to be 0, 3, 1, and D is 0, 0, 1. So what we're going to do is find the distance from C, so from this point here to this plane of AFH. So I want to find this distance in here. So to do that, I need to find the Cartesian equation of that plane. So I'm going to have my two vectors on the plane, which will be, I'm going to go HA, which is going to be the vector 2, 0, 1, and vector B, which will be HF, which is the vector 2, 3, 0. And then I'll get the normal by doing the cross product of those two. So 0 minus 3 is negative 3, 2 minus 0 is 2, and 6 minus 0 is 6. So I have negative 3x plus 2y plus 6z plus d equals 0. And I need to just sub in any of the points here, either h or a or f. I'm going to sub in h because obviously that one's pretty easy with it being 0. So D is 0. So this equation of the plane is negative 3x plus 2y plus 6z equals 0, or writing it in proper form, eliminating that leading negative. So here's the equation of my plane, and I'm going to have the point C that I want to find the distance is 0, 3, 1. So I'm just going to add in (3x minus 2y), is that minus or plus, minus 6z equals 0, and the point is 0, 3, 1. So if we were to find the distance from our point to our plane, that's the absolute value of what happens when we sub these x, y, z pieces into the Cartesian equation of the plane. So it's 3 times 0 minus 2 times 3 minus 6 times 1 over the magnitude of the normal. So it's 3 squared plus negative 2 squared plus negative 6 squared. So here we get the absolute value of negative 12 over the square root of 49, which actually works out nice. And remember, distance is always positive, so the distance is 12 over 7. And then the last one, we want to find, we have a plane where A, B, and C are the x-intercept, y-intercept, and z-intercept of the plane. So that's where this plane crosses the x, y, and z axes. And we want to say that the distance from the origin to this plane is given by this equation. So first of all, whenever I know that I want a distance from a point to a plane, I need to find the plane in Cartesian form. So I know 3 points. I know A is the x-intercept, so that's A, 0, 0. The y-intercept is B, and the z-intercept is C. So now I have 3 points, and we're going to figure out what the Cartesian equation of this plane is. So vector, let's say, points A, B, and C. I'm going to find A, B. I need two direction vectors. These are just points. So that will be negative A, B, 0. And let's do AC. Again, negative A, 0, and C. So now I know that the normal is going to be AB cross AC. So I'll do the cross product here. Negative A, B, 0. Negative A, B, 0. So when I do this cross product, it's BC minus 0, which is okay. And then 0 minus negative AC, so it's AC. I'll take away that minus 0. And then I get 0 minus negative AB, so plus AB. So the normal to this plane is going to be BC, AC, and AB. Those are the components of the normal. I can figure out what the Cartesian equation of the plane is. I'm actually just going to use another. So write down my normal. We had BC, AC, and AB. And I know that I have points A0, 0, 0, B0, and 0, 0, C. So I'm going to figure out the Cartesian equation I'm losing track of my variables here of this plane. So here I know that this is going to be BC times X plus AC times Y plus AB times Z plus D equals 0. And I will sub in any one of these points. I might just go with that one. So that's BC times A plus AC times 0 plus AB times 0 plus D equals 0. So D is equal to negative ABC. We see this is 0, and if I bring that over to the other side, it's negative. So my equation of my plane is, BC, BCX plus ACY plus ABZ minus ABC equals 0. That's the Cartesian equation of the plane with those x, y, and z intercepts. From there, I want to find the distance from the origin to the plane here. So remember, my distance is the absolute value of the point plugged into the equation. So this is going to be BC times 0 plus AC times 0 plus AB times 0 minus ABC over the magnitude of the normal. So this is the magnitude of the normal. So this would be BC squared plus AC squared plus AB squared. And we can simplify this a little bit. On the top, we would have the absolute value of ABC. You could have a negative there, but the absolute value, it doesn't actually matter, over B squared C squared plus A squared C squared plus A squared B squared. So that's what the distance from the origin to that plane is. That's all of this work before we even really start our proof. So what we want to prove here is that 1 over D squared equals 1 over A squared plus 1 over B squared plus 1 over C squared. So I'm going to start on the left side 1 over d squared. Now, I had this whole thing that d was equal to. So I'm going to sub that in, that this is 1 over the absolute value of a times b times c over the square root of b squared c squared plus a squared c squared plus a squared b squared. Whoop. And this is squared because it's not asking me for d, it's asking me for d squared. So now I'm going to square this. Good things are going to happen because the square, if I square an absolute value, I don't have to worry about whether it's positive or negative. And also that'll get rid of this big square root sign. So I'll just have the inside stuff here. Additionally, I have 1 over this. So if you're dividing by a fraction, you're going to flip it and multiply. So if I have like 1 over 3/4, that's like 1 over 1 times 4 over 3, which is just 4 over 3. Really, I flipped the bottom and got it out from under that 1 on top. So I'm going to do that. I'm going to flip this fraction that's on the bottom and square it. So on the top, I have b squared c squared plus a squared c squared plus a squared b squared over, and now I will have a squared b squared c squared, squaring each individual factor in that absolute value. So if I have a bunch of things added up in a fraction, I can pull apart each one and write them with common denominators. And then hopefully you guys are kind of starting to see. Then I will have a bunch of stuff that cancels. Oh, canceled the wrong thing there. So then this is equal to 1 over a squared plus 1 over b squared plus 1 over c squared, which is the same as the right-hand side. So that's it. I will have a Google Meet at 11 o'clock tomorrow, and you're welcome to add things to the homework Jamboard if you have any questions before then. You can also shoot me an email. Have a good night, everybody.